In this class, I will explain you how to develop a global stiffness matrix for a truss element. So, in the last video, I had explained you how to get the stiffness matrix for a two-noded bar element with 1 degree of freedom at each node. So, here in this case, I will take a truss element in general with some inclination with x-axis. So, this is the truss element. 1 and 2 are the nodal points, and the corresponding displacements here q1, q2, q3, q4. So, you have 4 translations in this case, general case. So, here we are going to derive the global stiffness matrix for the entire member with respect to the global coordinates by using the local stiffness matrix which we have already derived for a bar element. So, I will consider an element 1, 2 like this, which makes an angle theta with the x-axis. Now, from the diagram, you can see that cos theta will be, this is x2 and this is x1. So, this is x1, this is x2. So, x2 minus x1 divided by hypotenuse length of the element, that is cos theta, which I will take it as L. Cos theta I will derive it as L. Similarly, sin theta will be y2 minus y1. So, this is y1, this is y2, entire thing. y2 minus y1 divided by Le gives the value of sin theta, which I denote it as M. Le is the length of the element. Now, there are two matrices here. One is the nodal displacements in local coordinates, which I will call it as q dash, and nodal displacements in global coordinates, which I will call it as q. And to get this q dash from q, we have to use a transformation matrix called L. So, the transformation matrix is given by Lm 0 0 0 0 Lm, that is cos theta sin theta 0 0 0 0 cos theta sin theta. Like that. You can always derive this. Anyway, it is not required here. You just remember this. This is the transformation matrix L, which transforms this global nodal displacements in global coordinates to nodal displacements in local coordinates. Now, the derivation starts like this. We have to start from the concept of strain energy, as we did in the earlier case also. Strain energy for a truss element in local coordinates, it is the same as the strain energy for a two-noded bar element which we have derived earlier. So, here I will take this as strain energy as U is equal to, according to the definition of strain energy, it is half into Q transpose into Ke dash into Q dash. Please note down here, this is important. So, this expression is important. So, here U is equal to half of Q dash transport into Ke dash into Q dash. Here Q dash is given by L into Q here, and Ke dash is given by the stiffness matrix for a bar element which I have derived in the last class. Because the stiffness truss element in local coordinate will be the same as a two-noded bar element. So, stiffness matrix for a bar element with 2 degrees of freedom total. So, it is taken as K dash. Now, if you substitute this here, so what happens here, U is equal to half into Q dash is nothing but L into Q, transpose of that, into K dash is EA by LE into 1 minus 1 minus 1 1, which you have derived already. So, this you have to remember, into Q dash is once again L into Q. Now, from the property of matrix algebra, L into Q whole transpose will be Q transpose L transpose, that I have written here. It will be in the reverse way, half into that into EA by LE, where E is the Young's modulus, A is the cross section area of the element, L is the length of the element, 1 minus 1 minus 1 1 into L into Q. Now, here what I will do here is this QT Q transpose I will write as it is. All the other terms from here to here, I will make it 1. So that is EA by LE into L of T, L transpose into 1 minus 1 minus 1 1 into L into Q, like this. So this can be written in this fashion, half into K into Q half into Qt into K into Q. See, this is how you can write. So please observe here. So this is the strain energy due to strain energy in a stress element in local coordinates, whereas this is the strain energy stress element in global coordinates. So here, that is why this K is called as the global stiffness matrix for a stress element. So please note the difference between KE dash and K, or you can write it as KE. So, but it is in the global coordinate system. So, KE dash is the stiffness matrix for a ball element in local coordinate system, whereas KE is the stiffness matrix of the same stress element but with respect to global coordinates. So, that KE we have to find out now. So, KE is equal to this. So, KE is nothing but EA by LE into L transpose into 1 minus 1 minus 1 1 into L. Now, if you substitute and simplify this, you are going to get the global stiffness matrix. So, EA by LE is constant into L transpose. So, L is this. So, transpose of this we have to write. That means rows and columns we have to interchange. So, it becomes LM00 like this 00 LM. Then this will remain same into L will be once again this. So, I have written like that. Now, multiply the first two matrices. So, this is of the matrix, this matrix is of the order 4 cross 2, number of rows 4, number of columns 2. This is 2 cross 2. So, you can multiply so that the resultant matrix will be 4 cross 2. So, number of columns in the first matrix should be equal to number of rows in the second matrix, then only we can multiply. So, this becomes, when you multiply this, so you are going to get 4 cross 2 matrix. Once again, this matrix is 2 cross 4. So, when you multiply these two, 4 cross 2 and 2 cross 4, so this 2 and 2 should be same. Number of rows in first matrix, number of columns in first matrix should be equal to number of rows in second matrix. So, then the order of the product matrix will be 4 cross 4. So, please note that KE and KE dash is of the order 2 cross 2. So, this is 2 cross 2 matrix, whereas KE will be the order of 4 cross 4. So, that is global stiffness matrix for a truss element with 1 degree, with 2 degrees of freedom at each node. Please note that it is 2 degrees of freedom at each node, Q1, Q2, Q3, Q4. Like that we have to take. So, it is 4 cross 4. So, please note that the order of matrix, stiffness matrix, of course, order of stiffness matrix, what you get here is the same as number of displacements. So, since here there are 4 displacements, this will be of 4th order. 4th order means there will be 4 rows and 4 columns. The displacements are Q1, Q2, Q3, Q4. 4 displacements are there, independent displacements, 2 at each node. So, the order of stiffness matrix also will be 4th order. And another thing is, if you observe, it is symmetric. So, this stiffness matrix is always symmetric. That is by its property that you have studied in matrix and substructures. So, this is a symmetric matrix. Please note that all the stiffness matrix are symmetric matrix. So, whatever elements are present in the rows, it will be same elements will be there in the corresponding columns. So, this is also symmetric. You can see K dash is also symmetric. 1 minus 1 minus 1 1. This is also symmetric. Any stiffness matrix of any order, so it will be symmetric. That is the by characteristics of stiffness matrix. Now you have to remember this. So this gives the stiffness, global stiffness matrix of a truss element with 4 degrees of freedom in total. Now it is easy to remember this. So here please note that L is cos theta, M is sin theta, where theta is the angle made by the element in the anti-clockwise direction with respect to x-axis. That is very important. Now here, to remember this, it is very easy to remember this. So I will just divide this matrix into 4 parts like this, submatrices, 4 submatrices. You can observe here, if you remember the first submatrix, you can easily write the other 4 submatrices. So first submatrix is L square, Lm, Lm, M square. That is cos square theta, cos theta sin theta, cos theta sin theta, sin square theta. The same will be there here. Please note. So first and fourth, if I take this as fourth, first and fourth, they will be same. You can see L square Lm, Lm, M square, L square Lm, Lm, M square. Whereas the second and third, these two will be same with negative sign. All the elements with negative sign. So same thing, but with negative sign. Minus M square, minus Lm, minus Lm, minus M square. Same thing is repeated here. So that means this matrix can be easily remembered by dividing that matrix into 4 submatrices, where the first and fourth they are identical, second and third they are identical, but with a negative sign. This is how you can remember the stiffness matrix when you are doing the problem. So from the stiffness matrix, suppose if you want the stress matrix, so you know the relationship between strain, displacement and stresses. So last video I had explained this. For the stress sigma, the expression is Young's modulus E into B, where B is called the strain displacement matrix, into Q dash. So this is in local coordinates. This I have derived. So this I have derived already. You can just refer the earlier video. Now here for this Q dash, once again I can write L into Q, where L is the transformation matrix. Then B for a ball element, for a truss element in local coordinate. This also we have proved in the last class. I have shown this. B is nothing but, that strain displacement matrix is nothing but 1 by Le into minus 1 1 in the case of a 2-node ball element. 2-node ball element is the same as truss element in local coordinates, and here L is once again Lm 0 0 0 0 Lm. I have substituted that into Q will be there. So this is B, and this is L. Now once again if you multiply this and this, so this is of the order 1 cross 2, this is of the order 2 cross 4. If you multiply, you will get 1 cross 4. 1 cross 4. So 1 cross 4, this is 1 cross 4. So how to multiply? I think you know. So minus 1 into L, you have to write minus L. Then second minus 1 into L plus 1 into 0. Next minus 1 into M plus 1 into 0, which is minus M. Then minus 1 into 0 plus 1 into L, which is plus M. Then minus 1 into 0 plus 1 into M, that is plus M. So into Q, that will be there. Now this is the stress matrix for a truss element in global coordinates. So starting from local coordinates, we have derived the expression for in terms of global coordinates. So if they ask you to find the stress in the truss element, then we are going to use this expression. E is Young's modulus, L is the length of the element, L is cos theta, M is sin theta, and Q is the displacement, nodal displacement in global coordinates. So once you get the value of Q, you can always find out sigma using this expression. This is how the global stiffness matrix of a truss element with 2 degrees of freedom at each node for a 2-noded element is derived. So the difference between local and global is, so local coordinate means the along the length of the member itself, we are going to take it as the x-axis. It behaves like a one-dimensional element, whereas doing global coordinate, so irrespective of the orientation theta of the element, so global x-axis and global y-axis, they are considered as the axis of reference. So this stiffness matrix, the element stiffness matrix in global coordinates, you have to remember for analyzing problems in trusses.